and atmosphere, meaning vapor, and sigma phi alpha rho alpha, meaning sphere, is a layer of gases surrounding a planet or other material body of sufficient mass that is held in place by the gravity of the body. An atmosphere is more likely to be retained if the gravity is high and the atmosphere's temperature is low. The atmosphere of Earth is mostly composed of nitrogen. It also contains oxygen used by most organisms for respiration and carbon dioxide used by plants, algae and cyanobacteria for photosynthesis. It protects living organisms from genetic damage by solar ultraviolet radiation, solar wind and cosmic rays. Its current composition is the product of billions of years of biochemical modification of the paleo-atmosphere by living organisms. The term stellar atmosphere describes the outer region of a star, and typically includes the portion starting from the opaque photosphere outwards. Stars with sufficiently low temperatures may form compound molecules in their outer atmosphere. Pressure. Atmospheric pressure is the force per unit area that is always applied perpendicularly to a surface by the surrounding gas. It is determined by a planet's gravitational force in combination with the total mass of a column of gas above a location. On Earth, units of air pressure are based on the internationally recognized standard atmosphere, which is defined as 101,325 kilopascals. The pressure of an atmospheric gas decreases with altitude due to the diminishing mass of gas above each location. The height at which the pressure from an atmosphere declines by a factor of E is called the scale height and is denoted by H. For an atmosphere with a uniform temperature, the scale height is proportional to the temperature and inversely proportional to the mean molecular mass of dry air times the planet's gravitational force per unit area at the surface of Earth. For such a model atmosphere, the pressure declines exponentially with increasing altitude. However, atmospheres are not uniform in temperature, so the exact determination of the atmospheric pressure at any particular altitude is more complex. Escape. Surface gravity, the force that holds down an atmosphere, differs significantly among the planets. For example, the large gravitational force of the giant planet Jupiter is able to retain light gases such as hydrogen and helium that escape from objects with lower gravity. Secondly, the distance from the Sun determines the energy available to heat atmospheric gas to the point where its molecular thermal motion exceeds the planet's escape velocity, the speed at which gas molecules overcome a planet's gravitational grasp. Thus, the distant and cold Titan, Triton, and Pluto are able to retain their atmospheres despite relatively low gravities. Interstellar planets, theoretically, may also retain thick atmospheres. Since a gas at any particular temperature will have molecules moving at a wide range of velocities, there will almost always be some slow leakage of gas into space. Lighter molecules move faster than heavier ones with the same thermal kinetic energy, and so gases of low molecular weight are lost more rapidly than those of high molecular weight. It is thought that Venus and Mars may have both lost much of their water when, after being photodissociated into hydrogen and oxygen by solar ultraviolet, the hydrogen escaped. Earth's magnetic field helps to prevent this, as, normally, the solar wind would greatly enhance the escape of hydrogen. However, over the past 3 billion years Earth may have lost gases through the magnetic polar regions due to auroral activity, including a net 2% of its atmospheric oxygen. Other mechanisms that can cause atmosphere depletion are solar wind-induced sputtering, impact erosion, weathering, and sequestration, sometimes referred to as freezing out, into the regolith and polar caps. Terrain. Atmospheres have dramatic effects on the surfaces of rocky bodies. Objects that have no atmosphere, or that have only an exosphere, have terrain that is covered in craters. Without an atmosphere, the planet has no protection from meteors, and all of them collide with the surface and create craters. A rocky body with a thick atmosphere does not have significant craters on its surface. The friction generated when a meteor enters an atmosphere causes the vast majority to burn up before hitting the surface. When meteors do impact, the effects are often erased by the action of wind. As a result, craters are rare on objects with atmospheres. All objects with atmospheres have wind and weather. Wind erosion is a significant factor in shaping the terrain of rocky planets with atmospheres, and over time can erase the effects of both craters and volcanoes. In addition, since liquids cannot exist without pressure, an atmosphere allows liquid to be present at the surface, resulting in lakes, rivers and oceans. Earth and Titan are known to have liquids at their surface, and terrain on the planet suggests that Mars had liquid on its surface in the past. Composition. Initial atmospheric composition is generally related to the chemistry and temperature of the local solar nebula during planetary formation and the subsequent escape of interior gases. The original atmospheres started with the radially local rotating gases that collapsed to the spaced rings that formed the planets. They were then modified over time by various complex factors, resulting in quite different outcomes. The atmospheres of the planets Venus and Mars are primarily composed of carbon dioxide, with small quantities of nitrogen, argon, oxygen and traces of other gases. The atmospheric composition on Earth is largely governed by the byproducts of the life that it sustains. Dry air from Earth's atmosphere contains 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.038% carbon dioxide, and traces of hydrogen, helium, and other noble gases, but generally a variable amount of water vapor is also present, on average about 1% at sea level. The low temperatures and higher gravity of the solar system's giant planets, Jupiter, Saturn, Uranus and Neptune, allow them more readily to retain gases with low molecular masses. These planets have hydrogen-helium atmospheres, with trace amounts of more complex compounds. Two satellites of the outer planets possess significant atmospheres. Titan, a moon of Saturn, and Triton, a moon of Neptune, have atmospheres mainly of nitrogen. When in the part of its orbit closest to the Sun, Pluto has an atmosphere of nitrogen and methane similar to Triton's, but these gases are frozen when it is farther from the Sun. Other bodies within the Solar System have extremely thin atmospheres not in equilibrium. These include the Moon, Mercury, Europa, Io, and Enceladus. The atmospheric composition of an exoplanet was first determined using the Hubble Space Telescope. Planet HD 209458b is a gas giant with a close orbit around a star in the constellation Pegasus. Its atmosphere is heated to temperatures over 1000 K, and is steadily escaping into space. Hydrogen, oxygen, carbon and sulfur have been detected in the planet's inflated atmosphere. Structure. Earth's atmosphere consists of a number of layers, summarized in the diagram at right, that differ in properties such as composition, temperature and pressure. The lowest layer is the troposphere, which includes the planetary boundary layer or peplosphere at its base. 3/4 of the atmospheric mass resides within the troposphere, and the depth of this layer varies between 17 km at the equator and 7 km at the poles. The stratosphere, from 20 to 50 km, includes the ozone layer, located at altitudes between 15 and 35 km, which absorbs ultraviolet energy from the Sun. The mesosphere, from 50 to 85 km, is the layer in which most meteors burn up. The thermosphere extends from 85 km to the base of the exosphere at 690 km and contains the ionosphere, a region where the atmosphere is ionized by incoming solar radiation. The Karman Line, located within the thermosphere at an altitude of 100 km, is commonly used to define the boundary between Earth's atmosphere and outer space. The exosphere extends from about 690 to 1,000 kilometers above the surface, where it interacts with the planet's magnetosphere. Each of the layers has a different lapse rate, defining the rate of change in temperature with height. Other astronomical bodies such as these listed have known atmospheres. In the Solar System: atmosphere of the Sun, atmosphere of Mercury, atmosphere of Venus, atmosphere of Earth, atmosphere of the Moon, atmosphere of Mars, atmosphere of Ceres, atmosphere of Jupiter, atmosphere of Io, atmosphere of Callisto, atmosphere of Europa, atmosphere of Ganymede, atmosphere of Saturn, atmosphere of Titan, atmosphere of Enceladus, atmosphere of Uranus, atmosphere of Titania, atmosphere of Neptune, atmosphere of Triton, atmosphere of Pluto. Outside the Solar System: atmosphere of HD 209,458b. Circulation. The circulation of the atmosphere occurs due to thermal differences when convection becomes a more efficient transporter of heat than thermal radiation. On planets where the primary heat source is solar radiation, excess heat in the tropics is transported to higher latitudes. When a planet generates a significant amount of heat internally, such as is the case for Jupiter, convection in the atmosphere can transport thermal energy from the higher temperature interior up to the surface. Importance. From the perspective of the planetary geologist, the atmosphere is an evolutionary agent essential to the morphology of a planet. The wind transports dust and other particles which erodes the relief and leaves deposits. Frost and precipitations, which depend on the composition, also influence the relief. Climate changes can influence a planet's geological history. Conversely, studying surface of Earth leads to an understanding of the atmosphere and climate of a planet, both its present state and its past. For a meteorologist, the composition of the atmosphere determines the climate and its variations. For a biologist or paleontologist, the composition is closely dependent on the appearance of the life and its evolution.